All right, the general transformations worksheet started out with a long division here for us. So we did that with the area models. The x minus 2 is the thing we're dividing by. This is in descending order of power, so we want a 3x cubed to land there, which means this must have been a 3x squared, which would force this to be a negative 6x squared, but we're supposed to have negative 5x squareds, which means we must have needed a plus 1x squared there to make that happen, which means this must have been a plus x, which would have made that a minus 2x, but those x's were supposed to add up to 3x, so I must need 5 of them here. And if that's a 5x, then this is plus a 5. I just hit the constant, so everything else I run into now is going to be remainder. That's a minus 10, so the remainder must have been a plus 3. And so my answer is 3x squared plus x plus 5 plus 3 over x minus 2. All right, let's see, simplify and write with no negative exponents. Okay, well let's take this negative 2 in, and I'm going to deal with the negative. I could do it in a number of different ways, but I'm going to go ahead and just take everything inside to the negative 2 power, and then I'll do some simplifying. So that's it, 3 to the negative 2, an x cubed to the negative 2 is an x to the negative 6, y to the negative 4th to the negative 2, negative 4 times 2 is 8. And then I have a negative 2 to the negative 2, and x to the negative 2, and a y to the negative 3 to the negative 2, which is positive 6. Okay. The numbers are going to mess with me a little bit more here. So 3 to the negative 2 means that that's actually a 9 in the denominator. 2 to the negative 2, well, negative 2 squared is 4, and this negative in the exponent, the negative here disappears when I square. The negative here means move it into the numerator. So that's a 4 over 9. I want no negative exponents. So if I did negative 6 minus negative 2, I would still end up with a negative 4. So I'm going to start on the bottom and do negative 2 minus negative 6, or negative 2 plus 6 leaves me an x to the 4th in the denominator. And I definitely have more y's in the numerator than the denominator. The 8 minus 6 will give me a 2, so this is a y squared. And that is that simplified with no negative exponents. All right, into the transformation part. Identify the parent function, list the transformations that have been performed. I'm going to do that by creating an arrow diagram. So I start with the x. It looks like the first thing that's happening is division by 5. And then the negative shows up in front of that, so I'm going to do a sign change there. And then I add 3 on. All of that then gets cubed, multiplied by 2 on the outside, and then finally 1 subtracted from there. Here is my parent function. This is the only arrow that doesn't describe a simple transformation. So my parent function is x cubed. It's the cubing function. My transformations on the horizontal side, I have here, it looks like a shift left 3. I have a reflection over the y-axis. Horizontal reflection requires a vertical mirror. And a horizontal stretch by 5, and then I'll vertically stretch by 2 and shift down 1. So, describing those, again, as I move away from the parent function, I have a shift left 3, reflect over the y-axis, and horizontally stretch. Horizontally doesn't start with an S. get a horizontal stretch by 5, and then I'll list my vertical ones. Vertical stretch by 2 and shift down 1. That order will definitely work. I could have done the vertical ones first and then the horizontal ones, and that order would have worked as well. Okay. All right, write an equation for h of t, which is a transformation of f of t equals 600 times 1.005 to the t over 12 by horizontally compressing by 6, shifting right 12, and vertically stretching by 5. So I'm transforming this function called f, so I'm going to make the arrows for f. It started with a t, and the first thing was to divide by 12, put that in the power of 1.005, and then multiply by 600. Now I want a horizontal compression by 6. So horizontally over on this side, compress by 6 means divide by 6. Shift to the right 12, that is a horizontal thing as well. So right 12 is a plus 12, and vertically stretch by 5 is going to be multiplied by 5 at the end. So I want h of t, so I'll start with the t. I'm going to subtract 12, multiply by 6, and I will just kind of follow this all the way through and see if there's any obvious simplifying that I can do. So we're going to start with the t minus 12. That's going to get multiplied by 6 and then divided by 12, and then put into the power of 1.005. Then multiplied by 600 and multiplied by 5. Together that's going to be multiplied by 3,000 out in front there. And I can do a little simplifying here. And so it looks like my final answer for h of t is going to look something like, what did I say, 3,000 out in front times 1.005 raised to the t minus 12 over 2 power. All right, let's see. The next one here, write an equation for w of z, which is a transformation of v of z by shifting up 5, left 8, and horizontally stretching by 4, and then reflecting over the x-axis. So I'm transforming v of z. I don't know exactly what that looks like, so I'm just going to put v of on an arrow, and I'm going to shift it up 5, which is a vertical change. We'll move it up 5. To the left 8 is going to be a minus 8 on the horizontal side. Horizontal stretch by 4, so multiply by 4 on the input side over there. A reflection over the x-axis makes a vertical change because I have a horizontal mirror, so the sign change there. This was about z, so I'm going to put z in at the beginning, and it's going to say start by dividing by 4, and then add 8, stuff that into v, add 5, and change the sign on everything. So I've got a z over 4 plus 8, and v of that. Add 5 and change the sign on all of that. So my w of z, if I simplify that a little bit, that's going to be a negative v of z over 4 plus 8. The minus will distribute to that as well, so minus 5. This is what w of z looks like. All right, the dotted graph over here is the function p of x. The solid graph is the function q of x, which is a transformation of p of x. So write an equation for q of x based on p of x. Okay. Well, let's take a look at what is going on here. Okay. It looks like I've got this one sloping side, and in my function q of x, which is the transformed one, that's got a positive slope, but over here it's got a negative slope. So it looks like if I were connecting some points, that this point probably connects to that point, and this one connects to that one. So there has definitely been a reflection here. I can see also that my original function was looking at the markings on here. This is at -1 and goes to +1. So my original function was too tall, but this one is 1, 2, 3, 4, 5, 6 tall. So it looks like there has also been a vertical stretch. So I've got a reflection over the y-axis and a vertical stretch. Let me kind of start with that, and let's follow some points along and make sure all the points end up in the right spot as we're doing this. So I've got my original function, which is p, and the points that I know on p, I'm going to grab the important points that I would need to know. If I know where these points go, then I know how this graph goes. So it looks like there's 1, 2, 3, 4, 5, 6, 7 points that I need to keep track of. First one is at -2, 0. The next one is at -2, -1. And then I'm at -1, -1. And then at -1, 1. Clearly not a function, fails the vertical line test, but that's all right. I've got a point at 0, 1, a point at 1, -1, and then finally a point at looks like 2, -1. The things that I've definitely identified so far is I know I need to make this thing 3 times as tall as it was, because it was 2 vertical spaces before and now it's 6. So if I make it 3 times as tall, that's going to change this to 0, -3, -3, 3, 3, -3, and -3. And I was going to reflect over the y-axis, right? So that was a sign change this direction. Kind of crowded things in there a little bit here. That's going to give me a 2, 2, 1, 1, 0, -1, -2. Okay. Let's see, horizontally, this looked like it took up 1, 2, 3, 4 spaces this way, the original. And I am 1, 2, 3, 4 spaces horizontally still, so there has been no horizontal stretch in this, and clearly there's been no vertical reflection either. So let's take a look at my coordinates here. The coordinate on this point, I've got points now at 2, 0, and if I go over to 2, 0, I've definitely got some moving that I need to do. I think the point's got to end up here. So we identified before that on the original point, the point that was at 2, 0 should end up back over here at -3, 1. So that was kind of my final point. The Did I ever put that point at 2 comma 0? Okay. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. There, so I didn't get the last point on here, but let's look at the first point. Okay. This first point that was at negative 2 comma 0, right here, is supposed to end up at 1 comma 1, which would require in this case that I add 1 here and that I subtract 1 here. And if I did that everywhere, let's check the next point and see what happens. If I do that, this says I'm going to have a point at 1 comma negative 2. And so if I go to 1 comma negative 2, that is this point right here. So that gives me that one. Subtract 1 here would give me a 0. Negative 3 plus 1, again, and it's a negative 2. Do I have a point at 0 comma negative 2? Yes, that's that point right there. So it seems to be drawing out all of the necessary points for me. So I think we've got it here now as the equation. So this would be a plus 1 coming back that way, and a sign change. So I'm going to have x plus 1, change the sign on it, put it inside of p. That's going to be a negative x minus 1 when I do that. Multiply by 3 and add 1. This should be what q of x looks like to make that. I could check that with the rest of my points, but all the points are hitting along the way there now, so I feel pretty good about that. Okay. All right, use key points on the graph of log base 2 of x to sketch a graph of negative log base 2 of x plus 4 minus 3. All right, so my arrow diagram for the thing that I'm trying to do, I have an x. I'm going to add 4. That goes inside of the log base 2. I change the sign and subtract 3. Okay. So for my parent function here, the key points that we drew, we said at 0 we were going to have a vertical asymptote. So it was undefined there. At I think we did negative 1. Did we do negative 1? I don't think we did, actually. We did the log of 1, which was going to be 0, and because the base is 2, log of 2 is going to be 1, and then it went off toward infinity. So changing the sign on a vertical asymptote doesn't change it. Moving a vertical asymptote up and down doesn't change it. Change the sign on 0 doesn't do anything, but subtracting 3 does. Negative 1 minus 3 is negative 4, and changing the sign on infinity makes a negative infinity, but subtracting 3 is still a negative infinity. And to move this direction then, it says I should subtract 4. So I'll get a negative 4, a negative 3, a negative 2, and this is still infinity. Okay. All right, so it says my vertical asymptote is now at negative 4. So if I go to negative 4, I now have a vertical asymptote there. I have the point negative 3 comma negative 3, which is right here. I have a point at negative 2 comma negative 4, which is down here, and it says as I go off to the right, it will head toward negative infinity, and so we've had a reflection on this logarithmic graph. It's going to go out this direction and do its vertical asymptote thing that direction, so that should be what the graph looks like. Apologize for the length of that video, but there's a lot of stuff going on in that one.